Hi everyone, my name is Kayleigh Arthur and I'm a Senior Applications Chemist here at Alstone. So what I'm going to try and talk to you today is a new approach to breath biopsy at Alstone. So, oh, there we go. Slight technical difficulties. Okay, so the goal of breath biopsy at Alstone is to discover, validate, and to collect, discover, and validate biomarkers. So the thought processes are that the volatile organic compounds measured on people's breath can be indicative of metabolic activity in some of the presentations you've seen this morning. So the idea of breath biopsy is to try to make a standardized approach towards that end goal, both with the collection and the analysis of breath samples. So what do we actually need to do in order to do that? Well, we need an entire platform that's reproducible, sensitive, and robust. So our breath biopsy collection kits and Casper portable air supply are there to try to help us provide a high sensitivity by reducing and minimizing background noise, combined with our receiver breath sampler to collect breath samples that then get sent back to our breath biopsy laboratory. So our breath biopsy services workflow towards that end goal is to train clinicians with our receiver collection equipment to collect breath samples using our preconditioned standardized breath biopsy kits, including sorbent tube cartridges and masks. These samples then get collected by the clinicians alongside subject metadata at point of clinic. The samples and the data get sent back to the laboratory, where we analyze the samples using our standardized analytical methodologies, which go through to comprehensive discovery analysis using feature extraction and statistical analysis, combining with our study metadata to produce an end product for our studies. What we're trying to do, and what I'd like to talk to you about today, is the incorporation of the TD-GC-Orbitrap into that analytical workflow. So TD-GC-MS has been considered by Alstone as the gold standard for breath analysis for our breath biopsy platform. Collection of VOCs onto sorbent tubes to pre-collect breath samples and pre-concentrate them provide a wide analytical range, high abundance VOCs alongside trace level VOCs. So we need analytical equipment that can cope with the samples that we're collecting. So we started an ongoing R&D collaboration with Thermo Fisher Scientific to integrate the Q-Exactive Orbitrap into Alstone's breath biopsy platform. The idea being that this R&D project would qualify the mass analyzer, assess its ability to meet our breath biopsy platform, and advance the application of our non-invasive breath sampling to address some of the widely accepted challenges associated with breath analysis, that some of which you've seen this morning through the talks. So to speak a little bit more about the analytical workflow once samples arrive back at the laboratory. So our first steps are to receive those samples, analyze via a standardized sequence creation, and collect data from the breath samples using our TD-GC-Orbitrap. The new addition that's coming alongside the introduction of the new instrumentation is a dual analysis approach to do discovery untargeted analysis alongside a targeted analysis. Benefits of that is that we can use the targeted analysis to quantify the performance of the instrumentation and the breath sample collection, as well as providing a discovery analysis to look for those novel biomarkers and produce feature lists that can go on to statistical analysis and provide data for clinical interpretation. So the goal of this is to standardize the underlying analytical platform to allow features to be both detected, identified, and interpreted in order to produce an end breath biopsy study report. So I'm now going to talk not about the collection or the clinical challenges, but the analytical challenges in actually analyzing breath samples on TD-GC-MS. The breath samples that we collect are complex. there's a lot of information acquired onto the sorbent tubes coming from multiple places. We alluded to a collection of blanks this morning, the background VOCs, as well as high abundance VOCs such as acetone and isoprene. So typical concentrations of different chemicals and analytes can easily span 4 to 5 orders of magnitude. So our analytical methodology needs to keep up with these complex samples. So when we're producing the methods and the analytical standardized approach, we need to try to balance the requirements of selectivity, sensitivity, and scan speed of our analyzer and detector. So the introduction of the Orbitrap allows us greater control over mass resolution. The AGC target allows us to deal with those high abundance ions and not overwhelm the detector. Maximize data scan rate for the deconvolution and feature discovery, as well as, if need be, the combination of data-independent and data-dependent acquisition in a single scan analysis, combined with the high-resolution mass accuracy of the instrumentation. So to focus on the high-resolution accurate mass, why is that important to us? Well, it's crucial for metabolomic analysis and identification of chemicals, particularly low-concentration chemicals in the complex matrix. So the ability to achieve sub-1 ppm mass accuracy across the width of a chromatic peak means to 4 to 5 decimal place accuracy, you can track that particular ion over the course of a chromatographic peak, producing accurate mass spectra that from the lowest level to the highest level is stable ion ratios. So you can say, if you track multiple ions across a single peak, that those ions could be related and piece together the fragmentation pattern that the electron ionization produces. So that's all important for our untargeted discovery analysis, right? So the crucial challenge for this, for feature detection in particular, is reliable and reproducible deconvolution. The mass accuracy guarantees that the samples that we analyze will be reproducible to a very accurate mass. So our deconvolution needs to keep up to be able to track them through the sample. So we've partnered with Thermo to beta test the new software Compound Discoverer, which has been around for a while. So the new aspects are in the 3.1 version was the incorporation of the deconvolution software into the statistical analysis. So we have a single software for our untargeted approach. It also includes the option to embed custom scripts, such as Python and R, which was very valuable to Alstone as a lot of our statistic packages are built on Python and R. And the ability to export a flat feature table is quite important to us because it allows us to identify and track a feature within the same sample, across samples, and across studies. So using unique identifiers of the retention time on our platform, the mass to charge to high accurate mass, and the response in this demonstration peak area. So the first step we wanted to do in our R&D analysis was to verify that the output of the deconvolution of the complex matrix works. So if you put in targeted chemicals, so you prepare chemical standards, analyze them, but run them through the untargeted deconvolution software, do you find all the targets you put in? So far, we've had a very high success rate, 32 out of the 33 that we input. That is to say, the one that we didn't find was actually a perfect coevolution event. Any deconvolution software would have struggled to pick that up. So we're very happy with these results thus far. All of that is so crucial to clinical interpretation because it's all very well and good to find a chemical, but as Olaf just demonstrated in the previous presentation, the identification is what becomes important for clinical interpretation. Just seeing VOCs go up and down in study groups isn't enough. You need to be able to try to interpret where they came from and if they could be part of the clinical interpretation of the study. So the Orbitrap with the accurate mass brings us a high-resolution filtering option and fragment prediction. So if you library search your fragmentation pattern for your feature, find a hit, it can then, from the formula that's produced, go back and predict which fragments should be there. If they are, it gives you a super high confidence that that feature is the ID that you're saying that it is. Right? So this then allows comparison of compounds of interest that are ID'd across samples between studies. If you're looking for butanol in one study and you find butanol in another, the accurate mass library gives you the option to say that was the same chemical on different days in different studies. Now this can also be combined with the NIST library, so we can use standard libraries alongside the high-resolution libraries at the same time. So what we've been doing so far, we've started the creation of an accurate mass library on our Breath Biopsy platform. So to do that, we first analyzed chemical standards on the TD-GC-Orbitrap. We used the deconvolution and compound discoverer to predict the fragment ions and theoretical masses to identify a compound. We add that accurate mass spectrum to our custom Breath Biopsy library, and then we can use that back in the software to say, this compound from breath is that compound, in this case, 2,5-dimethylfuran. Some more examples of this working in breath. So to the left, we have 1-nonene. Now, alkanes, alkenes, they can be very hard to ID because they have very similar fragmentation patterns. It's often the ion ratio that becomes important in identifying them. And limonene, I mean, we've seen talks this morning already of the clinical importance of limonene, particularly for our EVOC probes. So being able to identify this to a very confident level is very valuable to us. So that's using the library and the accurate mass in a very untargeted way, but it can also be used for our target analysis, for our quantitation. So by using the accurate mass library spectrum as a reference, we can extract peaks with confidence within known retention time windows, which then allows us to calibrate our target and quantify it across studies, across days, across samples. And again, just to make sure we extracted the right thing, we can compare it against the library once extracted. So I'm just going to flash this up here for a few minutes or a few seconds, just to show some of the compounds that we've already started adding to this library over the past few months. There's some compounds of interest that have been mentioned this morning, such as the aldehydes, limonene. Hoping this will be available afterwards if people want to delve in more depth. I will say, however, that the examples I've shown you so far also work across instrument. The breath samples I showed there, the library was built on one instrument and compared to another. So it gives us high throughput capabilities as well. Which leads me nicely into the next topic. The fact that breath biopsy isn't just for a single study. I didn't animate the label there, so you know what's coming up. We want to offer this as a service laboratory, so we need to be able to have high throughput capacity. We need instruments we can rely upon that don't need continuous maintenance. So the hardware is the first step of the Orbitrap and was one of the biggest appeals because the ion source can be removed, changed, and cleaned all without breaking vacuum, which means it's reduced downtime and minimal user interaction for our analysts in the laboratory. The option of the dual filament is great because if one goes down, we can still run the instrument until we need to change it. And software as well. So alongside the new instrumentation, we're also going to start implementing the Chameleon chromatography data system across the breath biopsy laboratory. So this software is important to us because it provides data integrity. It's a single software to manage our analytical processes, control our instruments, store our raw data, and report results, all in one software. So this is allowing us to link instruments, even across laboratories. We can implement control of users and provides integrity of our data. So to give some examples, so instrument control. The ability to control the Marks TD, the TD-GC, and the TD-Orbitrap in the same software in a single sequence can't be understated for the simplicity it provides our analysts. It also provides system suitability checks at point of acquisition. So combining it with our targeted data processing, we can look for those targets, apply limits, and at point of analysis have those limits applied to the data If something erroneous were to happen and the test fails, it will pause the sequence, preserving the breath samples from these sick people that it takes a lot of effort and consideration to set up and acquire. Alongside that targeted analysis, within Chromeleon, we can automate calibration. We can have checks of our QCs throughout the system. And this is what then feeds back into automated monitoring and the system suitability tests to protect our samples. Monitoring of those QCs so far has produced very good intra and inter-sequence variation. I've overlaid 2 sequences here for the performance of Octane to show that even at an absolute level, the response has been very stable, but the quantitative accuracy as well has been so far greater than 95%. Alongside all of that comes a full audit trail, a complete instrumental log, and user accountability. An example of a sequence audit trail, so for every single sequence ran, every single thing the instrument did, every time a user clicked a button, it's all recorded to be investigated if needed. User accountability as well. Within the software, we can set up roles and users to say an analyst can process and submit data for review, but a more technical data reviewer needs to look at that data, make sure all the system suitability checks are passed, ensure data quality, and then send that to approval for the lab manager, who in addition would be in charge of the administration console and setting up which users can access which part of the software. And to finalize, data reporting, so customizable reports, which can include the audit trail, the quantitative analysis, and full output of the system suitability checks, which can be automated. So in summary, we've been doing a lot of work in R&D to integrate the Orbitrap into the Breath Biopsy platform. The Orbitrap itself enables us to detect both high and low concentration analytes from VOCs in a single analysis, with the options for high dynamic range and flexible scan modes. The Compound Discoverer software allows us to deconvolute, do discovery analysis with confident identification of unknowns to go into further clinical interpretation. And the Chromeleon CDS software is revolutionizing our laboratory from instrument control, data management, QC processes, and automated reporting. So all of this has been done in collaboration with Thermo Scientific to further optimize the Breath Biopsy platform when samples arrive at our laboratory in Cambridge. Expectations of when we expect this to be available to customers is early 2020. The first study is going to start in January, and we expect to be rolling it out across the first half of 2020. So just to say, for more information about the Thermo Orbitrap, Christian from Thermo is here today on the booth outside. And for more information on Breath Biopsy itself, he was giving a talk tomorrow, our VP of Sales, for more information about how to get a hold of the kits and send samples to our laboratory for analysis. I've not been doing this work alone. This would be too much for one person, so I'd like to thank our collaborators from Thermo to start with, Christian, Julia, and Dominic, and also the Alstom medical team behind all of this, with a nice picture in front of the Orbies. Okay. Thank you very much.
So, any questions? Yep.
Thank you very much for your presentation. Igor Bezverki from Dijon, France. I have a small question about what comes before mass spectrometry, about GC. Can we play with the column, maybe using 2-column approaches? Do you look for this part also? Thank you.
Yeah, so we definitely have the functionality to be able to do so. What we focused on so far is developing a standardized platform for breath biopsy. So there's a standard that can be built upon, targeted or customized, depending on negotiation with our sales team. The first goal was getting something standardized that we can rely upon, that's reproducible, that we can start to build data upon. But yes, there is the functionality to do so.
Is there one other hand there? Yeah.
Any microphones? Working? Yeah, okay. Orbitrap is quite famous for the analysis of heavy, large molecules in film of proteomics. So what are the performances in case of the very small molecules, like many of those that are involved in breath analysis? For example, you made what would be the minimum size of the molecules so that you can investigate what would be the detection limit of the technique?
So to quote what we're using at the moment, we're using a mass range of 30 mass to charge to 450. For further info of how to push that, I'd advise speaking to Christian.
Okay, so the detection limit of what you had a library of molecules. Would
Yes.
be the detection limit of the method that you are using with those molecules?
Okay, so far the smallest molecule is probably pentane and acetaldehyde. We've not tried lower than that at the moment.
Okay, thanks.
One here.
Talking about libraries, Ted Popov from Sofia, Bulgaria. Talking about libraries, what is the number of compounds that you have on your list for targeted analysis? Is there an approximate number that you can give us?
Currently there are 50 compounds on the list. Addition is going to be an ongoing exercise based on study requirements. If there's anything we'd like to add, the creation of that library so far was 2 to 3 days worth of work. It's not a difficult process for us. So we currently have 50 targets. I believe 30 odd are shown on the list at the moment. It's going to be an ever expanding library.
Okay. Right, thank you, Kayleigh.
Okay.